Right, we're going to start with spring potential energy. So when we think about springs, there's a couple different terms that we need to, we need to be familiar with, right? These common terms. When I talk about springs or coils or whatever, this is what we should envision, right? We see them, lots of different places, I guess, but there are a few vocabulary words that we need to know with that. When we say a spring is static or at equilibrium, what does that mean? It's not moving. It's not been stretched or compressed, right? It's in its rest state. We'll call that equilibrium sometimes in a spring, right? It's not doing anything. When it's being compressed, that means we're smushing together. When we stretch it, it means we're pulling it apart. When a spring is both either stretched or compressed, what is it going to do?
Release it.
Okay, right? We're going to see a release of energy when we let go, but it's going to bounce back and forth until it gets to its static state or its equilibrium, right? So when we see a compressed or a stretched spring, that means we have energy stored in the spring. We agree with that, right? And what type of energy would that be if it's stored? Right, potential energy. So we see elastic or spring or coil potential energy that is stored when we have these springs. Okay? So this is our equation for the potential energy in a spring, right? A spring that's going to, move an object or, apply a force and move an object, do work on another object. 1/2 kx squared. K is something new for us. Yeah, I would put that on your equation sheet. Mm-hmm.
So when you let go of the spring, is that kinetic energy?
Right, when the spring gets put into motion, it would have kinetic energy then. But when it's at its compressed state or stretched state, you would have only potential.
Okay.
Yep, and then halfway through your motion, you would have both. And then, All right, so our K is what we call a spring constant. And the fact that it's called a constant is a little deceiving because each individual spring has its own value for spring constant. Okay, it's not ones you'll have to memorize. But what the spring constant tells us is basically how springy it is. Right, how rigid the coils are or how loose the coils are. Okay, so that's a K value. We haven't quite gotten to its units, how they're derived, but the units for K are newtons divided by meters. Newtons divided by meters.
So in this situation, K isn't kinetic energy.
K is not kinetic energy. Lowercase k is a spring constant. Newton divided by meters, that's just the units for K. All right, what do you think the x value probably stands for? What is that x variable probably going to tell us? Distance or displacement that the spring has been stretched or compressed. How far is the spring from its static position? And that needs to be measured in meters. Good. So let's think about this for a second. Right, so usually springs are probably not going to be stretched or compressed a whole meter, right? It's usually going to be centimeters. So that's going to be a common one that you're going to have to convert to meters. Okay, usually we're not going to get springs that compress or stretch a whole meter, right? That would be a lot. But you'll need to make sure that we're converting on that one. So yes, that is one to be kind of careful and thoughtful about, but X should be measured in meters. Okay, let's see. All right, I want to talk just a little bit more about our spring energy before we get started. I want you to envision a spring that has been compressed. Right, here's my compressed spring. And like there's something on the end of it. Right, think of like a Nerf gun. Right, Nerf gun with a little Nerf bullet on the end. When you pull the trigger, that spring is released. And what does it do to the bullet? It shoots it outward. So what happens in that case is all of the energy stored in the spring is then transferred to the bullet, which moves forward, right? So what type of energy does that bullet have at that point? kinetic, right? We've had a transfer of energy. So the spring would become its equilibrium state, which means it would have no energy, and all of that stored energy from the spring is transferred to the bullet in a kinetic energy format. Does that kind of make sense? How you see that? It's just the same amount of energy. Whether it's 100 joules stored, that means the bullet would then have 100 joules worth of energy, right? But it can be a different type. Do we see that relationship? So that's what we're going to start doing next, is we're going to talk about mechanical energy, which is the total energy in a system. Total energy in a system. Okay? The sum of any kinetic and potential energy of a system at any moment. I don't want you to write that down right now. Okay? The total energy in a system, bless you, at any moment. Okay? So let's look at a roller coaster example, right? Here's my roller coaster. Halfway down its path. At this point, what type of energy does it have? Kinetic, potential, or both? Both, right? It's in motion because it's halfway down, and it still has the potential to fall farther, so it has both. Yeah. Not yet. I don't need you to have this on your equation sheet just yet. We're going to work to expand this a little bit further. But if I wanted to find out how much energy is in this cart right now, I need you to understand that it would also be the same amount of energy that was in the cart here, and it's the same amount of energy that was in the cart here, right? We don't lose or gain energy. Right? Remember, we're living in perfect physics world, which means we're not losing heat due to friction. We're not losing other stuff, right? We live in perfect physics high school world, right? So the energy amount in that cart is the same at the beginning, the middle, and the end. But what's different about the energy is that it's split different ways, right? At the top, we said we would have all potential, and at the bottom, we would have all kinetic. But in the middle, we have a combination of the two, right? So here, we would take 1/2 m times v squared plus m times g times the height of the vehicle at that point, and that would be able to give us the total energy in the cart. Does that kind of make sense? Okay, we need to remember that sliding scale of kinetic plus potential. It's always going to be a combination of those two at any point. Okay, we could also change out, if we're looking at a spring, it could be, sorry, I don't want this yet. It could be 1/2 mv squared plus 1/2 kx squared, right? It's any type of potential energy. So you just need to make sure we're focusing on, is it a spring or is it a potential energy due to gravity, right? All right. So we can combine our change in energies to form one equation for the conservation of mechanical energy. And I want to rewrite this here just a little bit. But essentially what's happening is that we're saying if energy is conserved, that means that my energy initial is equal to my energy final. We agree with that? That means in my roller coaster example, the amount of energy that's stored in our roller coaster at the top is the same amount of energy that it has at the bottom. It's just a different type of energy, right? It goes from potential to kinetic. But the amount of joules, let's say they have 1,000 joules here, it's also going to have 1,000 joules worth of energy at the bottom, right? That is conservation of energy. And so we're going to take this concept of conservation of energy and we're going to be able to say the kinetic energy at the beginning plus the potential energy at the beginning equals kinetic energy final plus potential energy final. Do you see how we expanded that equation? We know that the total energy is kinetic plus potential, and so we're just expanding that out. This 4-term equation is what we're going to use a lot, and I'm going to show you kind of what I think you should put on your equation sheet here in just a second. Okay? But we're going to look at this conservation of energy equation a lot in this 4 terms. I think I have it on the next slide here for you. Any questions about the concept of conservation? Energy at the beginning has to equal energy at the end, but they can be in different forms. Okay. All right, I don't want to talk about that. here is what I think could go on your equation sheet, right? We know that energy initial equals energy final, which leads to kinetic plus potential, which leads to this guy right here. This four-term equation, which is kinetic plus potential equals kinetic plus potential. Okay? You can put the ones here if you want, or you could make that initial and final if you wanted to, right? However you want to label that is up to you. I usually just really think about the left-hand side of the equation is before and the right-hand side is after. So I usually don't even include the I or the F, but we think about left side is initial, right side is final.
Is that like E at the bottom?
Give me one just a sec. Which one right here?
Yeah, the half and being 1.
1/2 mv squared. This is just telling me it's my initial velocity. Yeah. Okay. This is using gravitational potential energy, so this is things falling, rolling, doing whatever. If I was going to use a spring, and I was looking at conservation of energy with the spring, I'd go 1/2 mv squared plus 1/2 kx squared equals 1/2 mv squared plus 1/2 kx squared. Do we see the difference there? The only change is that instead of gravitational potential energy here, I'm using spring potential energy instead. Okay? What if my equation, or what if my problem had to do with a bungee jumper? It's a vertical spring. What would happen there? Would it have gravitational potential? And would it have spring potential? Yes. So you would just use 1/2 mv squared mgh plus 1/2 kx squared. You can have both types of potential energy in there. That's not a problem we'll see very often, but if it was a vertical spring, you would just have 3 terms over here and 3 terms over here. Does that kind of make sense? Okay. The good news is with this 4-term equation, it's pretty rare that we would have all 4 terms, right? Usually we're going to be talking about, at the beginning of the motion, here's my roller coaster, right? We start here and we want to know something about this spot. But at the top, I have all what? I have all potential, which means if I was looking at this problem, I would just drop that, right? I would say 0 plus my mgh equals whatever, right? The good news is that within these 4 terms, a lot of the time I'll be able to drop at least one of those terms, right? Especially if we're just looking at beginning and end. Okay? Question about the equation or how we manipulated that? Okay. All right, we want to think about a couple of things here. When we're looking at our energy, we're going to know that by the time it gets close to the ground, or the instant before it hits the ground, we're talking about a transformation of total kinetic energy. So here, right, we've got all KE. We're not going to talk about when it hits the ground and comes to a stop. Right? We're looking at the instant before that. Okay, it should have all been transformed into kinetic energy. So go ahead and get written down what you need to. I think it's helpful to draw a little mini diagram, right? So I'm going to kind of do that here off to the side. All right, these are types of problems that could theoretically be solved using a kinematics equation, but we're still focusing on our conservation of energy, so we'll use those equations to help us solve. But I want us to start thinking about what type of energy does my system have at the beginning? Right here, what do we have? All potential. Oh, I didn't put, it's just a dash. Sorry, not a negative. Okay, we've got here all potential, right? It's being held, number one, so we're not in motion, which means we can't have kinetic energy. At this 1 meter above the ground mark, what type of energy do we have? We have both, right? Kinetic and potential. Because we're still in motion, right? We're still falling, but we haven't reached the ground yet, so we still have the potential to fall farther. Does that make sense about what types of equations we have? All right, so if I go to my conservation of energy equation that says kinetic plus potential equals kinetic plus potential, I know at the beginning of my motion, my kinetic energy is 0. Okay, I like to put a 0 there so I know that I've thought about it, right? I didn't just forget. And then I've got what type of potential energy here, spring or gravitational? Gravitational. So I'm going to go M, which they didn't give us the mass, so I'm just going to leave it as an M for right now, times gravity times my height. Okay, my final kinetic energy, 1/2, I still don't have M, so I'm just going to leave it. I'm solving for V. Okay, and then I've got M times 9.8 times my height. Okay, I'm going to point this out real quick so that we can think about this. We could also have called this the ground and made my initial distance 2 meters and 0. Does that make sense? You can shift that up. If that doesn't make sense to you, then just forget I said it. But I'm just telling you, for those of you that were probably thinking it, yes, you can.
So if we did that, then that side would be...
Right, it would be just kinetic energy at the end, no potential, because my final height would be 0. Right. So for those of you thinking it, yes, you can. Okay. All right, let's go ahead and solve here. I've got an M and a V squared. Does that seem problematic? As of right now, it does. That's right. So let's go ahead and solve the algebra, and I'll show you what happens. All right, 9.8 times 3. That gives me 29.4 M equals 1/2 mv squared plus 9.8 m. Okay, do we see, where can I go from here? I can subtract over, right? I'm going to combine like terms. So minus 9.8 m minus 9.8 m. I think that gives me 19.6 m equals 1/2 mv squared. Now do we see what can happen? I can just divide by m, right? My m's will cancel here, because I've got only multiplication terms on both sides. My m will cancel. Then from there I'm going to do 19.6 divided by 1/2, or times 2. And then I need to do what last step? I need to square root that, because this is v squared, so I have to square root that. I came out with negative 6.3 meters per second. Right, why negative?
Because it's going down.
It's going downward. Right, that you have to add. Assuming the height of the roller coaster is 40 meters and the car starts from rest, calculate the speed of the car at the bottom of the hill. At the top of my coaster, I have what? All potential. And at the bottom of my coaster, I have all kinetic. Okay, so as I go to set up my equation, my initial kinetic energy is 0 plus mgh. I want to solve for kinetic, so 1/2 mv squared. My final potential energy is 0, right? I like to include the zeros so I see all 4 terms and I know that I really thought about it. Then I can go plug in numbers. We weren't given a mass again. I'm just going to leave it out. Okay, this one is tough. I think of a roller coaster's motion as forward or backwards. So it's not in free fall, so I keep it positive. It wouldn't be one that I would count off if you did put it negative, because you're right, theoretically it is going downward also. But I generally think of roller coasters as kind of just moving forward. Does that make sense? Right, right. So yes, they were moving downward, but I usually keep roller coaster ones positive. Good question. Okay, questions about how we solve that? All right, we're going to extend this problem a little bit. At what height will the car have half of this speed? So at what height will the car have already gained half of its speed? The cart is going to be somewhere in this range, right? When it picks up half of its speed. We agree? It's not going to be at the top and it's not going to be at the bottom. So that means at the beginning, we're still just going to start with no kinetic energy plus potential. Right? We're still starting at that 40-meter height. But at the point where it's halfway, it's moving at half that speed, it's got to have both types of energy. Agreed? So 1/2 times, what's my velocity? Half of that speed. 14. Plus m, which we don't have, that's okay, times g times the height. That's what we're solving for, right, is the height. I just left the m's off because we weren't given mass and we know they're going to end up canceling. So I left it off. Now we just solve our algebra. Right, because eventually we would combine like terms here. We would have subtracted that over, and then it would have given us something m plus, or equals something m. You know what I'm saying? There would have been only multiplication terms on both sides. We would have had to combine like terms in there. I just skipped that step.
So
Does that make sense?
Yeah.
Okay.
is it okay if we leave it out like in a problem?
If it's given to you, put it in, right? But if it's not given to you, that means it's going to end up canceling, right? Unless you're solving for it. But did we get a height of 30 meters? So does that mean 30 meters down the hill? Or that means 10 meters down the hill? 30 meters what? Off the ground. 30 meters off the ground, right? We're saying our height started at 40, but then our height at 30 is when we picked up half of our speed. That's why on a roller coaster you feel that rush at the beginning, right? You've already gained half your speed at only a quarter of your way into your trip.
Why wouldn't it be halfway down?
That's just how it works. I don't know. That's why you feel that rush, right? It's not just falling, falling, falling. You gain a lot of speed at the beginning and then you finish. Okay. I want to show you one thing. I want to prove to you mathematically that we have a conservation of energy. So we started our system with 392 joules. If I take 1/2 times 14 squared, that gives me 98 plus 9.8 times 30, 294 plus 98 is 392. So I want you to see that mathematically there is a conservation of energy, right? We started with 392 joules of energy, and then at that 30-meter mark, we still had 392 joules of energy. Okay?
So we can use that to like double check on.
Mm-hmm. You want to try this spring one on your own? You want to do it together? It's a lot of words. All right, we'll do it together. That's fine. All right, a dart with a mass of 0.1 kilograms is pressed against a spring. The spring is compressed 6 centimeters. If the dart detaches from the spring and reaches normal length or reaches equilibrium, what speed does the dart acquire?
Is it always going to give us that value?
The K value, it'll either give it to you or you'll solve for it. Yes, it'll give you everything else. It's not, K values you'll never have to memorize because every spring has its own value.
Is the normal height or the final?
The equilibrium, right. So here is equilibrium, right here. And then it's been compressed 6 centimeters, right? So here it's been compressed at the beginning. So this is my start, and this is my finish. It's been compressed at the beginning. When it's released, the dart happens to be released at the exact time that it hits its equilibrium, okay? So in that case, it makes our problem a little bit easier. But at the start, what type of energy does it have? When it's coiled like this, 6 centimeters, what does it have? Only potential. So my kinetic is 0. What type of potential does it have? Spring or gravitational? Spring. So 1/2 times K, oops, times x squared. And what did we say we had to be careful with x? Needs to be meters, right? So not 6, but it needs to be 0.06 squared, right? We're really careful with our units for our x value.
Why does that mean?
Because in order for the K value to work, the K was measured in newtons divided by meters, in order for the K value to be true. Okay, then at the end of our motion, the spring has reached equilibrium and all of the energy has been transferred to the dart. So the dart has what type of energy? Just kinetic. So 1/2 times the mass of the dart times velocity squared. And we said there's no potential energy to end the problem. Okay, so now it's just an easy solve from there.